you so much for coming. Tonight we're going to hear a talk from Elli Papangelakis. And her talk is titled Chaos, Heraclitus, and Rivers, Finding Order in a Complex World. So Elli obtained her bachelor's degree in physics from the University of Toronto. Now she's doing a master's of science in geography here at UBC. She studies fluvial geomorphology and sediment transport, in simple terms, why rivers are shaped the way they are, how sediment moves through them, and how they evolve in response to environmental changes. So to answer her current research questions, she combines methods borrowed from the fields of fluid mechanics, statistics, geography, civil engineering. In the past, she's enjoyed applying her background to numerous interdisciplinary problems, which makes her a great fit for here at Green College, including archaeological, medical, and hydraulic projects. And something you might not know about Elli is when she was growing up, she was actually an elite gymnast. And when she was 14, she was #1 in Canada. So maybe she'll do a backflip. No, I'm just kidding.
I'll not be doing any backflips.
All right, so join me in thanking Elli and ready for a great talk.
Okay, so today I'm going to talk about a variety of different things, and I just want to point out that I'm not going to be just talking about my own project. I'm actually going to be talking about some bigger picture themes and questions that have kind of come up in my last few years of doing research. And I will talk about my project and how it fits into these bigger pictures, but I just want to point out that hopefully this is kind of interesting because it's going to be more of getting people to think about some things maybe a little bit differently. So my main theme is going to be order versus chaos in nature and how we can deal with it and why it comes up. So one cannot talk about chaos without talking about Lorentz. So Edward Lorentz is known as kind of the father of chaos theory. And I want to talk a little bit what I mean when I say chaos. So when I talk about chaos and chaotic systems, I don't mean random systems. So we're not talking about things that happen at random. We're actually talking about something a little bit more exact than that. So I'm going to start with a bit of a story. So Lorentz was a famous meteorologist, physicist, mathematician, and he was kind of around when people first started using computer models to model the atmosphere. And what he did is he created a really simple model to kind of show how gases are going to move in space. So you came up with these 3 equations, which are actually relatively simple. I mean, they're just adding and subtracting terms. The top one is for circulation, so the air actually moving, and the bottom 2 represent kind of how the temperature is distributed across them. So they're actually pretty simple. And what he did is he plugged these into a computer model, gave some initial conditions, and said, play. And he actually found that his computer could predict at a later time, at any time, what the conditions were of the system. And he's like, oh, that's really cool. I'm going to do it again just to make sure that it works. And a few times later, when he tried to do it again, he actually found that he got a completely different result. And he was like, hey, I don't really know what's going on. So he kind of looked back into what he did, and he realized that he actually plugged in different conditions at the beginning, but they were only like 1/100th different than the original one that he did. But that small difference was enough to give him completely different results. So when I'm talking about chaotic systems, they're actually not random at all. They actually follow the laws of physics, but they're just very, very, very sensitive to changes in the initial conditions. So this shows 3 different runs of a simulation, and they actually start off really, really similar, and it shows how for a little while they kind of behave the same way until you get to a certain point, and then they diverge completely, and you start getting completely wild results. So this is kind of why we can't predict the weather past a few days, because our weather systems are chaotic. They're nonlinear, which is another kind of word to describe it. So this is kind of where the butterfly effect comes into idea, that a butterfly flapping its wings in Cancun can cause a tornado in Texas, because that very, very small change in air pressure that the flapping butterfly creates will magnify later in time into a giant storm. So that's kind of, so are we dealing with evil butterflies? I don't know. So back to this for a little bit. Yeah, the other problem with this is that because it's so sensitive, any errors that we have here will create giant errors here. So theoretically, if we knew the temperature, airspeed, humidity at every single point in space all the time, we could probably predict the weather a lot better than we can, but we can't. All our measurements have some error in them just by the tools that we use, and those errors mean that we can't really predict too far into the future. So some other examples of chaotic systems in nature. This is a satellite image of an island off the coast of Sweden, and these are actually bioluminescent algae on the surface of the ocean. And you can see, it's color enhanced, obviously, but you can see that the motion of the water is very turbulent. Turbulence is a very well-known chaotic system. It's very hard to model, very hard to predict how the water is exactly going to move. Actually, it's kind of cool. You can see these are boat tracks, which is kind of cool. Anyways, as a side note, this is from NASA's Earth as Art project. You guys should look it up. It has a lot of really cool false image pictures that are really pretty. But that's just a side note. So water moving, air moving, those are all chaotic. Geologic processes like erosion, those are all chaotic. Things like landslides, when will the next landslide happen? We don't really know. So what does that mean for us? Well, like I mentioned, it means we could know all these physics very, very well, fluid mechanics perfectly. We can have the most sophisticated models, but in the end, we can't predict this. This is a channel in Argentina. This is where the channel is now, this blue one, and all these other things are what we call meander scars. So those are places in the landscape where the river used to be, but now has moved. So rivers are constantly adapting and shifting and changing. And these could be thousands of years old, tens of thousands of years old even. So even if we understand rivers really, really well, unfortunately, we can't predict exactly where they're going to be. We can make some good guesses, but we will never really know. This is another really famous example. This is from the Parana, I hope I'm saying the right, river on the Argentine-Paraguay border. And it's pretty famous because it's a shared resource, and it's very, very chaotic, which causes problems if you're trying to share it and if you're trying to use it as your border, because it keeps changing. And there's a very famous case which happened a few years ago. There was a giant log jam, so a bunch of trees falling into the river, which kind of backs up the river, and they kept growing and growing until one day, in just one day, it was large enough to stop the flow, and the river actually changed 90 degrees and started going completely into the one country, which was a problem. And then they tried to build canals, and it was just a mess. But that just kind of shows the chaotic nature. That one extra tree that fell in that no one could predict when it would fall caused this entire system to change. So what does that mean? Does that mean we're in trouble? I mean, can we never really know anything? Do we just live in this world of chaos, and who knows what's going to happen next? Well, we actually have a few tools that we can use because we can't just accept that we live in a chaotic world. I mean, we need to build flood structures that are good enough. We need to build buildings that are good enough. So we have a few tools that we can use to get around this. One is using probabilities. So this is a flood frequency graph, and it shows the probability of a flood of whatever size you want happening. So in this example, it's showing a flood of 1,800 meters cubed per second. It has a 10% chance of happening each year. So that's kind of one way to go around it. We collect data for tons and tons and tons of years. We do stat analysis on it. And we can't know when the next flood will happen, but we can have an idea of how likely it is to happen. Another way we do this is we run multiple models multiple times. So this is a model that is trying to predict the course of a hurricane. And basically, these are all different models that are slightly different. And what they do is they run all these models over and over and over and over again, changing different things like the water temperature, the wind speed. They keep like hundreds, thousands of times they keep running this. And then they can say with reasonable confidence, OK, it's most likely to go this way, but I mean, it could go as far as here, but we're going to plan for the most likely. So that's kind of how we get around it. So recently I've been reading, just on my own time, a book on ancient philosophy, and I came across something that really reminded me of this. I was reading about Heraclitus, and he's a pre-Socratic Greek thinker, probably one of the most important pre-Socratic Greek thinkers. And his main theory was that the world's always changing, the world's always in chaos, and his famous quote is, "You can't step into the same river twice." So he actually he said, OK, I accept that. The world's chaotic. That's fine. It's always changing. That's just how it is. You can't really know the true nature of anything, so it's always changing. And I thought that that was just an interesting parallel to draw, that we still kind of think about the same things and have the same problems now. But let's just take a moment to think about this. Is this true? Is everything really just random? I mean, if you, well, not random, but chaotic. Sorry, my bad. If you believe that, though, you run into some problems pretty quick. The first problem is that if rivers, like I said, really are chaotic, how come so many rivers look the same? So this is a picture of the Amazon River from satellite. I just went on Google Earth and took these pictures. You guys could go on and find a million other rivers that look the same. And this is a picture of a river in Papua New Guinea. I don't even know what it's called. But that's exactly the point, that you can find just rivers all over space that look the same. And sure, maybe the individual bends and twists are different. But I mean, if you saw these two pictures, you wouldn't be able to tell which is which. So in some ways, how can that be? I mean, how can systems that are so chaotic end up looking so similar? Like, what is going on here? Is it a problem of scale, that we're just looking at a bigger scale, a bigger time scale? Or is there actually something about all those chaotic processes that when they add up together, bring some kind of order? And we don't really know. But this is a very interesting paper by Stolum, published in Science in 1996. What they did is they created a model for meander erosion. So they started with a flat river, and they plugged in some equations that describe how meanders form, and they just told it to run, run, run for 30,000 iterations. That's a long time. And they actually found that there were times where the model seemed to be pretty ordered, like the meanders would get bigger, but they would kind of follow a pattern. And then they would just, for no apparent reason, go into a chaotic state where the meanders were just completely all over the place. And they couldn't understand why. Like, why? I mean, what leads to this and what leads to this? Why does that happen? They wanted to investigate this further, so they decided to plot sinuosity. So sinuosity is a measure of how curvy the river is. So you're dividing the river's actual distance, so if you followed the entire length, versus like the straight line distance. So you're just basically measuring how bendy it is. And what they found is that the sinuosity, just as they predicted, was chaotic. It didn't really follow a pattern. It was all over the place, up and down. But what they found is that if they looked at large enough iterations later, like 30,000, and took the average, this is kind of freaky, at least to me, but they found that the mean sinuosity was actually 3.14, which is the sinuosity of a circle, which is actually pretty incredible if you think about it. It's kind of creepy. So is something bigger at play here? Is it just a scale thing that we humans live in this little bubble, like that's our lifetime, so we can't really tell that the system's ordered? Or is there actually something about all these processes working together that allow the system to go from chaos to order? I mean, who really knows? No one knows. So to move away from meanders, this is just one example, I want to show you a few more landscapes that look really similar. This is the Brahmaputra River in India. This is actually just north of here in the Pemberton Valley, and you can see that they look kind of similar. I mean, this one is hundreds of meters wide. It's a huge river in kind of a flat plateau, whereas this one's in a mountainous area and is probably only 30 meters wide. But you can see that we see a lot of similarities. These are images of moving away from rivers. These are images of glacial landscapes. So all of these are from mountains. These were all carved out by glaciers, by ice. And I mean, if they weren't labeled, you probably couldn't tell which was which. Even a geographer probably couldn't tell which is which. But I mean, even if you look at the branching here and the branching here, like you can see that they look remarkably similar. This one's a fun one. So these are, I told you that wind is chaotic, yet you get sand dunes that look really similar. This is a sand dune in Namibia. Does anyone want to guess where this sand dune is?
Mars.
Yes, that sand dune is on Mars. So in fact, making the point that this is not something special about Earth. This is something is going on here, which is quite strange. The other problem that we run into, if you believe that all these systems are chaotic, are how come, if that's true, how come things are self-similar? How come things look the same at different scales? This is a picture of the empty quarter in Saudi Arabia. This is the largest sand desert in the world. Yes, larger than the Sahara. And this is a giant space of land. This is 10 kilometers, just to give you an idea. So this is a giant, this is a satellite image. But if you were to walk along these sand dunes, they would look something like this. So you get these ripple patterns at various scales. Just another example, this is an image of an empty river basin. So this river is dried up. This is about 160 meters wide, or that line is. If you were down on the ground, you would see this. That's a quarter. So you can see that these patterns, not only you see them across space, but you also see them in the same location across scale. So something is going on here. That's what we call self-similarity and fractals. These are all pictures of drainage basins. This is actually a real image of the Colorado River Basin when it's dry, or part of it. I know it looks fake. That's how cool Earth is. Basically, fractals describe patterns where, like the larger section of it looks like the smaller one, which looks like the smaller ones, and it keeps going down in scale. And we can actually assign a number to this called the fractal dimension, which describes how much branching there is, what the geometry of the branching is. And what they found is that they calculated the fractal dimension for thousands and thousands of river basins, and they found that they all fall under a very narrow range of fractal dimensions. So it's, again, the idea of all these rivers look quite different, but they all kind of follow some kind of order, where the stream is meandering, where the stream's in the mountains and the lowlands. I mean, that's kind of interesting. That's how they actually analyze Mars, and they can say, this feature on Mars was made by water, and we know that because it has the same fractal dimension as river basins on Earth, which I think is really interesting. Of course, rivers aren't the only ones to have fractals. Glaciers also cover fractal dimensions. So these are all glacial landscapes. They have a different fractal dimension, but again, very similar, and they can say, oh, this on Mars was most likely made by ice because it falls under the same fractal dimension as the ice ones on Earth. So what happened to all that chaos? Like, what is going on here? How come sometimes there is chaos and sometimes there isn't? That's really the big question. Again, reading from the philosophy I was doing on the side, I came across Parmenides, and he was Heraclitus' arch nemesis, and they had this huge debate, and Parmenides actually disagreed with Heraclitus and said, that's not true. Because if everything's always changing, then you can't prove that anything exists, because it just can't be. And he believed that change is actually an illusion, and humans just can't understand that the real world is unchanging and always the same, and change is just an illusion. That was his kind of theory. But is that true? Like, those are the two extremes. The real question is, how do these work together? So this is where my project comes in. I work on a much smaller scale than landscapes because you can't see landscapes change. They take thousands of years. And I'm not a modeler, I'm an experimentalist, so I need to measure things happening now. So I work with riverbeds, so the bottoms of rivers. They're not flat, they have ripples, they have different bed forms in them, and you can actually see these evolve over a pretty short time frame, so over the length of one flood, let's say. So they're kind of more easy to kind of use as a way to research this question. So I specifically work with these bed forms called riffle pools. They're kind of like giant ups and downs on the riverbed. And riffles tend to be shallow, the water's moving fast, the gravel's really big. And then the pools are deeper, the water's moving slower, they tend to have sand and silt. And you find these in rivers all across the world, all across space. They're very common. And they're very similar everywhere they're found. Even like the spacing, so the spacing from a riffle to riffle is always 5 to 7 times how wide the channel is, and that's always. So again, these are some kind of order that is happening on this channel bed. This is a picture of riffle pools. The screen's not very good, but this would be like a riffle, the water's fast and turbulent, and this would be a pool where the water's deeper and more calm moving, and you can see that there's another pool there. I'm sorry, the image is really bad, but yeah. And why they're important, aside from philosophical endeavors of chaos, is that salmon actually spawn in riffles. Salmon need very specific depth and flow speed and gravel size in order for their eggs to survive. So riffles are really important ecologically as well. And a lot of salmon are having trouble because population-wise, because a lot of these riffles are being degraded due to dams or land use. So the main application of my research would be to find a way in which riffle pools are formed so that you can rehabilitate streams or restore streams so that salmon can use them for spawning. So that's kind of the main purpose. So the way I do this is I actually study individual grains and how they move on the bed. So I actually track individual particles as they move down the stream, which sounds like a crazy endeavor, and sometimes I think it is too, but I'm trying my best. So let's look more into this problem. So think about how gravel is going to move. This is a rock on the channel bed, that's the water. And you have the water that's moving through. This is at low flow, and the water's not fast enough to move the rock, so the rock sits there for most of the time until a flood comes along that's big enough that can move it. So the rocks aren't always moving. They usually tend to move during high flows or floods. And when they do move, they usually move in a series of steps. So the rock will be picked up from the water, it'll move a bit, it'll stop, it'll get picked up again, move a little bit, and stop. So that's kind of what I'm trying to observe and work with. I can show you guys a video. This is from the lab. You can try to pick out a few rocks and try to see this motion sort of happening. So you can see that the rocks are being picked up, moved, and then they stop again. So that's kind of what I'm trying to capture and what I'm trying to model in my research. So if I was to model this, can anyone think of the things I need to consider? I have a rock, and I want to predict whether it's going to move or not. What do I need to take into account? Alistair.
The rate of water?
Yeah, the water. Kevin?
The size.
The size of the rock. Anything else?
Density of it.
Density. Anything else? Okay, so that doesn't matter too much for my opinion. But the point is, I need to know everything about the flow. I need to know how fast the water is moving. Not only that, I need to model the exact, like what's happening in the flow at every point, which is turbulent, and we know that that's really hard. Then you may just have like a really strong burst come along, and it's really hard to model that. You need to know everything there is to know about the rock, its size, its shape, its density. And you need to know everything about all the other rocks, because, I mean, if you have a small rock, it can hide behind bigger ones, right? So if there's a small rock hiding behind a big one, it's not going to move. Or you need to know if something like this happens where all the larger rocks are on top and the smaller ones are hiding underneath. So, I mean, how the heck could we ever do this? I mean, how can you always know where every single rock is and always know what the flow is in every single point in time? This is impossible. And the first person to work with this problem thought so too, and that was Einstein. This is actually Einstein's son, so not famous gravity Einstein, but his son, who was also an academic, a little bit less famous, but he has a statue too somewhere. And he ran a bunch of experiments and observed this for a really long time. He came to the conclusion that even under the same experimental conditions, stones having essentially identical characteristics were transported to wildly different distances. It was therefore not possible to determine a regularity for the path of a given stone. So scratch that, it's impossible. Could never do that. So he said, okay, I'm going to think about this a different way. I'm going to think about this more with probabilities. So thought, okay, this rock's going to get picked up and move, and this is what this graph is showing. So the rock's not moving, it's going to move a bit, then not move, then move a bit. And he modeled this and he said that I'm going to assume that how far the rock moves each time it jumps and how long it waits in between are just completely random. I'm just going to assign randomness and create a completely probabilistic model for this, which he did, actually. It's a compound Poisson process, which has nothing to do with fish. It's kind of funny that, I mean, it's rivers and anyways. And this actually works really, really well. And people have tested this in the lab. They've tested it in the field over and over and over again. And it seems to work really, really well. I mean, the rocks do seem to move in this probabilistic way. But before we get too excited that we found the answer, I mean, how does we go from that to this? all the rocks really are moving around completely probabilistically, wouldn't you expect the bed to always stay flat? Because if all the rocks were moving randomly, they would cancel each other out and the bed would stay flat. This suggests that they're not moving around probabilistically. They're actually moving in some sort of pattern that allows the big ones to stay here and the small ones to group here. So, what the hell's going on? And that's exactly, this is an unanswered question, and this is exactly what my project is trying to do. So what I do is I have a flume. It's like it's a fancy word for a fake river, or modeled river, that sounds nicer. It's 18 meters long, it's filled with colorful sediment, and we track the rocks as they move through. And first I'll track them when the bed's flat, and then I'll create a riffle pool, and then track them as they move through the riffle pool and try to spot differences. And how I do that is I put an obstruction. If you narrow the channel enough, you will force the riffle pool to form. So I can actually keep tracking them as the bed moves from flat and the rocks are moving randomly to when the rocks start moving in the order of the bed. So I'm trying to actually capture that moment when that transition happens. What are the conditions? How long do I have to wait? How high does the flow have to be? Like all these questions is what I'm trying to ask. And I also have field data to kind of help me along. These are stones that have been in the field for 9 years now. And every year people go out and actually find them and map them out. So this is just from 1 year. But it's been going on since 2004. So this is supposed to be a scaled down model of this. But here we can actually make riffle pools form in just a matter of hours, whereas here you would have to wait for maybe a season. So it kind of makes it easier. I actually brought some show and tell. So I actually track the rocks, that won't stay there, in a few different ways. So the one way is I use fluorescent paint, which would be like this rock. And I use UV lights and make the lab really dark. And the the fluorescent ones are the only ones that show. And I can actually track them with a high-speed camera and use a software that can track their exact motion. And I can analyze that. What's going on in the field, which I also use in the lab, is these rocks, they have little tags in them with like electronic little tags. And they actually have unique IDs. So when you go out in the field, you go out with like this little metal detector thing, you can actually find the exact same rock. And that's how we use it to actually find them. And they're really useful because you can find them even if they're buried, and it's pretty cool. People can come look at them if they want. I know not everyone's as excited, you don't have to pretend, but I think it's really cool. So that's kind of what my project is doing. That's how my project is trying to link this chaos that we see in rock movement to the order that we see later on, and maybe try to find what the link is there. Sometimes I feel like this is a crazy task, and this is me, and I'm just going into a sea of chaos, and I'm trying to find things that aren't there. But other times the results are proving quite good, actually. So yeah, just to bring this back all to that philosophical debate we were talking about. So is nature completely chaotic and always changing, or is nature never changing? And, you know, things just always are, and it's just an illusion. Plato, which most of you know about, he actually brought those two ideas together. He read a lot about the philosophers before him, and he came to the conclusion that we both do and do not study the same person. So this is kind of what I'm working with. I mean, there both is and isn't chaos, and the whole idea is to try to figure out why sometimes there is and why sometimes there isn't. So that's my presentation.